Am I audible in the back? Yes, it appears like that. So, good morning. What were we doing in the last class? We were looking at mismatch and we were looking at how to mitigate them, how to reduce their impact. So, what kinds of mismatch are there? So, there are two kinds of mismatch that we talked about, uh, systematic and random. So, what are systematic variations and what are random variations? So, let's start with what are systematic variations. Variations whose impact is deterministic. Depending on the geometrical positioning of those devices, you can preempt the impact of those variations, and therefore you can model them. Such variations are called systematic variations. Then, which are random variations? They are intrinsic and statistical. They cannot be preempted. Like you may have a completely symmetric, or let us say a common centroid layout, exactly same structural matching also. But despite all of that, there will be some variations which are intrinsic to the process. And those cannot be modeled. They cannot be modeled means the variation can be modeled, but they cannot be predicted that this device will have this behavior and that device will have this kind of a behavior. Are you with me? So, how do you handle or mitigate the impact of systematic variations? See, whatever we are discussing is something which can be asked to you in any interview also. So, how do you mitigate the impact of systematic variations? Okay, so there was a shout out for resolution enhancement techniques. There was a suggestion that you would simulate the circuits and see what is the impact. Okay, what else? By leaving margins. Okay, what else? Yes, by designing in such a way that these variations don't happen in the first place. For example, we talked about uh, if if you have to track a bit line which is in metal 2, then the replica bit line should also be in metal 2, cannot be in metal 3. So this is a systematic variation which you will do by tracking, by ensuring that the design itself takes care of mitigating these. Even after that, something comes that is more random. But if you can do structural matching, if you can do so, common centroid is one way of handling systematic variations. Uh, Structural matching is another. Ensuring that they are in the same metal layer is one. Ensuring that the stress effect on the different devices that you want to match is same is another. Now, these are things that you can do as a designer yourself. Are you able to see this? There is no uncertainty in this. You can match stress effects, you can match well proximity effects. We looked at how we were designing the row decoder, the final stage of the final NMOSes of the row decoder stack, NAND stack, so that the well proximity effects are handled well. So that is the first thing that you have to do to mitigate the impact of systematic variations. Once that is done, then comes the point of modeling. That those variations, the technology team should model in the spice cards so that then you can simulate and see what is the impact. Are you with me? See, it's something like this. When you talk about being conscious of the environment, being very environmentally aware and stuff, people talk about recycling. But of the multiple R's, the first R is reduce. Reduce your consumption. That is the most important thing that you can do for the environment at any point of time. In the same manner, just design it in such a way that those variations impact both your match circuit and the original circuit in the same manner. Then you'd see how to mitigate it through other means. But first step is structurally match karo. Ensure that all these effects, which are systematic in nature, are reflected similarly for the match device and the primary device. Are you with me? Okay. Then what about random variations, systematic variations? Any questions? Hmm. Okay, we did talk very briefly about STI. Yeah, we said that in advanced technologies, we have shallow trench implants to separate two devices, NMOSes, PMOSes, whatever. To separate two devices, we have shallow trench implants. Now, do you realize that all the physics that we talk about in DVD first few lectures, if you remember, we started from the fact that silicon is a crystal. It is an infinite lattice. So all the assumptions of band gap, all the assumptions of everything else were made considering an infinite lattice. Are you with me? But in reality now, what happens when you do STI implant? Just after the device, so which is within few nanometers, few tens of nanometers of the gate region, जहाँ पे आपका channel बनने वाला है, within a few nanometers of the gate region, you have broken the crystals and you have put something else there. Now, as soon as you break a crystal, what happens? Now there are dangling bonds. There are dangling bonds there. Are you able to visualize this? And those dangling bonds still need to be neutered, they need to be handled. So something will happen. The density of STI could be a little more than, so STI also has silicon in it. It is silicon dioxide. So it could have a different density than silicon itself. All those, physical parameters, the fact that there are dangling bonds or the bonds that are now, instead of silicon connected to silicon, there is some interaction happening between silicon and an oxygen atom at that interface. So all those things imply or result in a differing behavior in the channel also. Because now that infinite assumption of a band gap is no longer true. So this causes some variations in the physics of the device. And those variations will be different depending on how far this break of STI is. Are you able to see this? So when you have very short active extensions, just contact लगाया और वहीं पे आपका active finish हो गया, then the STI impact is more pronounced. Then if you have a very long, for example, in a memory cell, I drew it the last time, when you are talking about NMOSes, pass gate and pull down is a long stack, continuous active. So the STI impact is reduced. Now, if you want to model a memory cell or replica of a memory cell needs to be created, you want to use the same structure there so that it also shows exactly the same behavior. This also necessitates another thing that we do to handle systematic variations related to stress. And we talked about the edge cells or the environment cells that we put around the array. You remember we talked about that last time? So why is that done? Again, that, okay, this is my real memory cell, but I have given a pair of environment cells above it, so that it sees a similar stress as other cells in the other rows. Are you able to see this? And it is not just about stress. Even word lines see similar density, bit lines see similar density. For every metal layer or every layer that you are designing, Keeping an environment cell ensures that the proximity is same. This is very, very important for memory cells, also because we do a lot of DRC violations. So the stresses that we are posing on the memory cells are very different from what would be happening in a DRC clean setting. So we want to replicate those DRC violations also for just a little more, so that those stresses do not just simply vanish. They remain there until the last column, until the last row. Are you with me? Does that answer your question, man? No. See, uh, again, as I said, we need to first understand the mechanics of it, that it will lead to a change in uh, the band gap and the structure of the physics that we were talking about. Now, you are talking about the stress effect because of STI only. But in advanced technologies, we also use very different kinds of stressors. Even on the gate, we use stressors. So I would not want to explain why, like this observation that when it is STI, this happens and that happens. Stress effect can be used to boost performance. And it is actually used to boost performance in a very significant way in advanced technologies. So अगर PMOS खराब हो भी रहा है, that is just because of that particular stress effect. Realizing that stressors, see, something that is detrimental can also be used to make something useful. वो है ना कहावत, if life throws lemons at you, make a lemonade. So when you already know that stress effect is going to happen, then make best use of it. So stress effect or stressors are used to boost device performance also in advanced technologies, even in PMOSs. So the physics is different in every case, and this we are not in a physics class abhi, so I'm not going into those details. Otherwise, यहाँ पे फिर लोग कहेंगे सर कोई कुछ भी सवाल पूछता है आप उससे भाग जाते हो. We can discuss that in the office hours. Okay, but again, it is closely linked to the physics, and we use stressors carefully. In fact, silicon germanium is used to stress. So a bilkul slight doping of germanium is done in silicon atoms. Now, what does that do? Germanium atoms are larger than silicon atoms. This you have done in your class 10, 11th, 12th physics also? No. Was it there? No. No. She's looking at me. No, nahi kara, sir. So germanium atoms are doped into silicon lattice because germanium atoms being larger cause a different kind of stress. The percentage of doping, 1%, 2%, 5% of germanium in the silicon lattice causes intrinsic stress inside silicon and can help in improving mobility or degrading it depending on what you're looking for. Is that okay? So don't think of it as a formula. What you notice is an observation. Don't make it rigid in stone. Are you getting it? Any other question on systematic variations? So we're actually going beyond systematic variations, but it's a valid discussion related to the topic. Okay. So then what are the random causes of random variations and how are random variations mitigated? No, first, what are the reasons for random variations? Random variations, you will realize, are mostly linked to manufacturing processes. We talked about line edge roughness. We talked about surface imperfections. We talked about random dopant fluctuation and how they are in the bulk technologies one of the most prominent sources of random variations. And how in FDSOI technologies or FinFET technologies, because you have a fully depleted substrate, this particular part of variations is completely taken away. In the last session, we also talked about how just taking away of random dopant fluctuations, same technology, so everything else, all other processes in terms of line edge roughness and everything else remained the same. We just removed random dopant fluctuation and we could lower the VDD min by 100 millivolts. Just so that is the impact. 100 millivolts VDD was raised just to ensure that random dopant fluctuations are mitigated. The effect of impact of random dopant fluctuations is mitigated. So multiple sources of random variations, and you will notice each and every one of them is linked to some process, some step inside the manufacturing process. Hmm? And even in FinFETs, we said, okay, because we went to fully depleted, the substrate random dopant fluctuations was removed, but the fact that your FinFETs can now be tapered, there is a vertical height, a different dimension, and the variations would start to appear because of that. We discussed that also. So as we move across the technologies, new sources of random variations may appear, again, depending on what is the process. And old ones may vanish, depending on what you have done with the process. How do you manage them or mitigate them? Now comes the answer that all of you are at once shouting in cohesion. How do you manage or mitigate random variations?
We can firstly make a statistical model of it, and then we can do the Monte Carlo simulations. It will give us a probability.
So again, तुम वापस jump कर रहे हो estimation of impact पे. सबसे पहले हमें ये देखना है how do we minimize by design, which is using large devices, using large lengths, larger widths. Now, do you see larger width has a direct impact on area? And area is diamond for memories. That is where in analog circuits, where area is not really a premium, they go for devices which are 10 micron wide, 5 micron wide. All of you have designed some analog circuits. They go for lengths which are 1 micron, hmm, 0.5 micron. They play with microns. You are playing with nanometers. So obviously the impact of random variations is far, far more accentuated when it comes to memories. The device sizes are by nature, by design, small. But despite this very strong constraint, you continuously see where can you increase the lengths, where can you increase the width so that the benefit of reduced mismatch can be maximally extracted. Are you with me? So that is the first thing that you do. Then, once the design part is taken care of, then you come to what Arpit was saying. That, okay, you model these variations, these distributions in your spice models. And then you simulate. And you estimate what is the impact of these variations on circuit performance, on circuit robustness, and then you leave margins for that. You ensure that come whatever may, the circuit would not fail. Are you with me? So as a designer, देखो आप till the time you're looking at it only as a person who has to manage a design, what Arpit said is the only thing that you can do. But when you are designing, you can be more resourceful. You have much stronger influence than just verifying there. And you should start on the right foot, saying that, okay, I want larger lengths. I want larger devices so that we can have reduced mismatch. Are you with me? Any questions about random mismatch and how to mitigate their impact? Sorry? So they are physical phenomena, like for example, when we talked about line edge roughness. It's a physical phenomenon, it's a chemical phenomenon that the crystals will be in this particular, they are polycrystals arranged next to each other. And as you etch, they have this anisotropic behavior around them. So you cannot simply have a smooth poly. There are bound to be variations. These are intrinsic phenomena. When we talked about random dopant fluctuations, uh, the depth at which an atom, a dopant would go and sit, the location where it will go and sit, whether it will be next to a silicon atom or far away from another one. We do not know. We can't control. Naturally, some they will get placed, they will get embedded somewhere. You will do annealing, something else will also happen. So that is what I mean by they are physical effects. They are happening because of the manufacturing process itself, and you really cannot have any control over it. Here again, because these random fluctuations, whether they are line edge roughness or surface imperfections or surface thickness, gate oxide thickness, as we go to advanced geometries, what happens? The instrumentation has remained same or similar. So that plus minus 5 nanometer in gate length, which was at 180 nanometers, not of much consequence. It was not even 5%. Hmm? At 14 nanometers, plus minus 5 would be almost 30% variations. So even with best or improved instrumentation, the percentage impact, the overall impact of variations is more pronounced in advanced technologies than it was in earlier ones. Are you able to see this? So, see, as designers, you will realize this once you join a company and start to do some designs. That backend में कोई भी technology चल रही हो, you will see people flaunting, oh, I've worked on 7 nanometers, I've worked on 5 nanometers, I've worked on 3 nanometers. As designers, you will not see any difference in the way you are designing, except variations. So now then you ask them the next question, okay, how did you mitigate variations? No, my role was only to do marginalities. Then they've done nothing. They don't know nothing about the new technology. They've just used the model and got done with the verification part of it. Okay. So mismatch is something that will lead to failures in advanced technologies. And that is where this particular chapter is extremely important. Those of you who have not watched the video yet, either the earlier ones that were recorded or the ones that we recorded last week, I would strongly recommend please go and watch. This has a far-reaching implication for you. Whether you become a memory designer or not doesn't matter. In advanced technologies, mismatch and mitigating that mismatch is going to be a really big job for designers. So you better uh, check this one chapter out. Is that okay? Any further questions about random variations or how to mitigate them? Yeah.
After this slide, there will be the lecture.
After this slide?
You will start the new lecture.
Yes.
Some questions of the quizzes. So there was one question of that which of the following statements are true. So one option was random mismatch cannot be eliminated, and this has been marked as false.
So we eliminated the random mismatches linked to random dopant fluctuations. We discussed that in the class.
Just eliminated the random dopant fluctuation by using FDSY.
One impact. So see, what it meant was that there can be some parts of random mismatches which can be eliminated.
Random mismatch cannot be eliminated. So it is true, right? Even in FDSOI line is roughness or something would be there.
Definitely. Oh, could be. It is there.
Yes, so
Could be. It is there.
so it can by using FDSOI and then it should be that random dopant fluctuation cannot be eliminated. Then
Okay. Understood.
one more.
See, you understand the concept. What I'm saying is that there can be technological changes through which some types of random mismatches will not even exist later. A new one will appear. So that was where the statement was intended to be. Doesn't matter. See, why are you struggling about those half marks and 1 marks? If you're asking about clarity on the statement, is the statement clear? Is the intention of putting the statement and putting it like that as an answer clear? Okay.
One more statement was there that LER can be reduced by increasing the device size. So LER doesn't reduce it. Its impact on the electrical characteristics.
Yes. Impact of LER, impact of mismatches can be reduced by changing the size. The physical LER, that is physical roughness, cannot be changed by changing device size. Physical roughness change करने के लिए you will need to use technological interventions. You will need to use smaller polygrains. You will have to use different chemicals for etching or different time, different dosage of your etching material. Yes.
So it was marked correct. It is not.
Yes. It should be the impact. The word should be impact there.
So there was one more, like what can be done to prevent excessive negative voltage on a bitline in small instances. So I have marked correct as lower coupling capacitance to the assist driver. Why it is not correct?
Mm, which were the options?
Injected negative charge.
Huh?
That is marked correct. Faster discharge slope of small bit lines.
That is inconsequential.
Then presence of residual positive charge at the time of assist.
That is fine.
And the fourth one is lower coupling capacitance to the assist driver, and it is marked incorrect.
Okay, that should be marked correct because that and the first option are related. Are related. That should be marked correct. Because in the first option, even if you look at the description that is given, the description does say that you change the size of the capacitance so that different amount of charge can be coupled onto the bit line. So that should be marked correct. Bapre. Yeah.
What is the need for statistical STA in advanced technology?
Mhm.
So the marked correct answer was that to model random mismatches only. So I have seen on internet like yesterday that statistical STA can be used to model the systematic variations as well, because in statistical STA delay is not considered as a number but as a function of variations forces. So they use something called spatial correlation model, and then they can model the systematic variations as well.
See, systematic.
Papers and I have marked as well.
See, it can be used as a hypothetical statement. The way it is used today, for example, how do I put it? Okay. The way the SSTA, the libraries for statistical analysis are made, they do not take into account systematic variations which could appear spatially. They only take into account random variations. So while you may have investigated this statement afterwards to see that, okay, mera answer sahi hai ki nahi hai, I would say that it is far superior and safer to say that we take care only of random mismatches in statistical analysis, because the libraries, if you really want to characterize the libraries with that hypothetical possibility कि भाई मैं spatial variation को भी ध्यान में रखूंगा, that doesn't really, because libraries are not characterized like that. The libraries are not characterized like that. The models to be able to do that are not made like that. The models that you use for your Monte Carlo simulations only include random variations. They do not include that space-related spatial variations because your tooling doesn't support that yet. It can support in the future, but today no. Are you with me? So again, hypothetically आप ऐसा कर सकते हो, but क्या आज support हो रहा है? नहीं, आज SSTA खाली ये कर रहा है. Is that okay?
Regarding the negative bitline point, so my what approach that we used in class was to find the negative voltage was that first we calculated the total charge that we made that on the bitline, then we divided by the capacity.
So that was utilizing the residual charge on the bitline to be able to do this.
Capacitance. So charge transfer will be more negative, but the capacitors. Yeah.
See, what you are doing is, see, the first obvious thing that you could have done is change the capacitance so that different amounts of negative charge would be injected onto the bit line. If the bit line capacitance is large, you would inject a larger negative charge on it. If the capacitance is small, you would inject lesser negative charge on it. But to be able to design and track, okay, how is the bit line changing? That is a arduous effort, and you would end up leaving more margins. So the second technique with the one second matlab, the one that we covered in the class was about using residual charge on the bit line itself, triggering while there was still some residual charge on the bit line, so that you can uh, ensure that the negative voltage that will finally appear on the bit line doesn't put the devices at risk.
No, but even if we have a smaller coupling capacitance, so that would result in the final charge being less negative, but that means we're injecting less negative. But that will also decrease the resultant capacitance that we have at the end, right? So
Why do you need? Okay, so what does writability of a memory cell require? When you do write margin analysis, you find that okay, nominal minus 6 sigma is minus 50 millivolts. What that means is that your bit line should carry minus 50 millivolts on it to be able to successfully write inside that particular memory cell. Are you with me? So, what is the bit line capacitance is not a consideration for us. That analysis is more of a DC analysis, where we say that if I keep minus 50 at the bit line, I will be able to write into the memory cell. So, I'm more concerned about what voltage is appearing at the bit line rather than bit line capacitance from the memory cell perspective.
yeah, but the method that we used in the last class for calculating the voltage, that depends on both the charge that is there finally and the total capacitance that we took of the right one and the right.
Okay, so the method is not something hi-fi. That method is not rocket science. That is the most fundamental foundational principle that we talked about very early on in our first year, second year courses, which is law of conservation of charge. We said that Bitline has this much residual charge. I am injecting this much total charge. This is my final charge on the Bitline capacitance. This is the total capacitance of the Bitline. This is my negative voltage. In the other scenario, you say, okay, Bitline has no charge on it because you always trigger after discharging the Bitline. Bitline has no charge on it, and I want to couple only that much that it results in minus 50 millivolts on the combined capacitance. So now I say that, okay, because it's a smaller bit line, I will have a smaller capacitance to inject that charge. But when it's a larger bit line, I will use a larger capacitance. So that effectively, whatever is the final capacitance of my bit line, I have minus 50 millivolts only. So वो मेथड कोई रॉकेट साइंस नहीं है माधव, दैट इज सिंपल. सो ये ध्यान रखना, many times in your interviews and your written tests, wherever, people will try to confuse you with different kinds of circuits. But essentially, what is happening is two capacitances are getting shorted. Immediately, the first thought is, what is happening to charge here? Because we're talking about capacitances, voltages are a consequence of charge. And voltages are not conserved, charge is conserved. तो आपको क्विकली चार्ज में मूव करना पड़ेगा ऐसी सिचुएशन में. Are you getting it? So I am still not able to understand why are you so worried about bitline capacitance? That is of no consequence for the memory cell perspective.
I was thinking in that sense that what we did basically was we calculated for calculating the final bit line voltage. We did the total charge that we have now and find total capacitance that will have about the combinations. So now if we suppose what we do is we decrease the capacitance that we have. So in order to inject less charge, the total charge will decrease, but the denominator, the total capacitance that we have, that will also decrease.
Yes. So that you can always mathematically estimate how much capacitance you need to bring it to minus 50 millivolts. That's a math thing, na? You're absolutely right. Go ahead. But that you can still arrive at. It's a mathematical iterative process. Worst of all. Is it okay? Should we move to the next part? We're now continuing with the statistics. We have looked at the fact that all these variations have a statistical basis to it. There are these Gaussian distributions that we talked about. There are all these things that we talked about. And now we look at what extent of the statistics you need to qualify for qualifying your designs. So this is the most famous distribution that all of you have seen. If the mean is at 0, you call it normal distribution. Otherwise, it is Gaussian distribution. Whatever is the target, that is where my peak of the bell curve will settle. And plus minus 1 sigma on each side will include a particular sample size. So in a Gaussian distribution, plus minus 1 sigma from the mean would include something like 68.2% of samples in it. Plus minus 2 sigma from the mean will include around 95% of samples in it. Plus minus 3 sigma, 99.7% of samples in it. तो 99.7 अगर आपका परसेंटेज आपके एग्जाम में आएगा तो दैट इज प्रैक्टिकली 100 फॉर यू. So you are happy? Plus minus 3 sigma करके. Memory is not. Because for memory cells, for example, how many memory cells will be there in a memory of size 1K words and 32 bits? How many memory cells will be there? 1024 into 32. 32,768. So now, अगर मैं उसका 99.7% निकालूं, तो how many of my memory cells are out of this plus minus 3 sigma range? Quickly do. All of you have phones which have calculators in it. How many samples are left out if I qualify plus minus 3 sigma?
980. No.
If I qualify plus minus 3 sigma for a memory of 1K cross 32, which is a very small memory. 1K cross 32 is a very small memory. छोटा सा cache ही है एक तरह से.
99 cells.
So एक नंबर यहां से आ रहा है कि लगभग 100 cells, 99 cells will not be qualified. Is 99 the number everyone is getting? So in a 1K words memory, 1K cross 32, 1K 32-bit words memory, 99 words. So 99 cells which could be randomly distributed. In the worst case, those 99 words would be impacted. So out of 1000 words, 99 words will fail. Do you think that is okay with you? Do you think you will get 100% marks when you qualify plus minus 3 sigma? You can't even make a 1K word memory work. How many of you have heard about Six Sigma process qualification by Six Sigma? किसने सुना है वो शब्द? So software companies में Six Sigma is a very strong, claim that okay, we are Six Sigma qualified. That is Six Sigma for you, plus minus 3 sigma. And do you realize for memory design that is absolutely irrelevant? You can't even make a small memory of 1K words work at plus minus 3 sigma. If your chip has an on-chip memory of, let us say, 16 megabit, which is not huge. अगर आप अपने फोन के जो आपके पास phones पड़े हैं, if you just look at the specifications of the application processor in that phone, you will realize it has more than 16 megabit on-chip cache. So every one of you is carrying more than that amount of cache in your pockets. Cache मतलब वो रोकड़े वाला cache नहीं, cache memory, okay? So each one of you is carrying that much. And to qualify that, you need plus minus 6 sigma qualification. You think for an enterprise server or a high performance design, you will need to go beyond plus minus 6 sigma. Not 6 sigma qualification, it is 12 sigma. In fact, I'm saying 13 sigma or 14 sigma may be required depending on what is the on-chip capacity that you're talking about. Now, if instead of memories, you are talking about PLLs, how many PLLs per chip? One or two? So if you would qualify 99 point plus minus 3 sigma, what would be the yield? You will still have an yield of around 99 point something. चल जाता है. So now do you realize that why is mismatch a much more critical challenge in memory design than it is in analog design? We already talked about the fact that our devices are not as huge as they are in analog circuits. Now we are talking about the sigma extent that we need to qualify. Now, I'm not saying that PLL teams would qualify only plus minus 3 sigma. They would also qualify more than this. But even with plus minus 3 sigma, they can at least pass. You can't even have one memory working if you do plus minus 3 sigma. They will have some respectable yield. आपका तो zero yield आएगा. Are you getting it? So that is the first thing that you need to internalize when you talk of handling mismatches, whether systematic or random, for memories. That is why matching is so critical and important in memory design. Okay? So, yeah, if you have to have 6 megabit, then plus minus 6 sigma gives you 99.999999998 something fails. And so now, because Gaussian distribution is so well known, uh, if you arrive at this conclusion that your SNM is Gaussian in nature or your right margin is Gaussian in nature, then all you need to find out now is a good estimate of mean and a good estimate of deviation. If you have that, then you don't really need to run 6 million simulations. 500 simulations will give you a stable mean and a stable sigma. So do this experiment for yourself in your projects. When you will work on your projects, many of you will be designing memory cells or doing sense amplifier design or something like this. You must be thinking of. Hmm? So just play with the number of Monte Carlo simulations, and you will see that mean would stabilize within the first 50 simulations itself. That whether you run 50 simulations or 100 simulations or 1000 simulations, mean will be practically within 1-2% of the very large number of simulations that you did. But sigma, depending on how big your circuit is or which technology we are talking about, might stabilize at 100, 200, or 500 simulations. Now, 500 simulations ho, chahe 1000 ho, chahe 4000 or 10,000 ho, you will realize that the sigma value changes within 1% of it. So it's a law of diminishing returns. And once you arrive at that stable value of sigma, you say that is the number of simulations that you have to launch to qualify your design. See, in analog design, they typically say that we will actually launch 1 billion simulations or 1,000 simulations or 10,000 simulations of my PLL to see that this doesn't fail. Now, for memories, you can't do that. It's physically impossible. You cannot have that much of a computer source to be able to launch that many SNM and then right margin, and that to not at one voltage and the entire voltage range. You can't simply do that. So you have to find a statistical method of analyzing your design. That is why statistics is a very important branch to understand and design robust memories. Okay? So if you have a stable mean and a stable sigma, and you know that the distribution is Gaussian, you're good to go. Is that okay? This is about analyzing your design. Now, another thing that memory designers need to be very careful of is the capability of the process. Because for others, it may not be that big an issue, but for memory designers, because you're talking about plus minus 6 sigma there, this can become an issue. So I'm just going to spend a few minutes on how process capability is understood. See, when we want to design transistors with a target VT, it may happen that some dosages may be up or down, and I finally have my peak of the bell curve, not at that target, but a little bit to the left or to the right. Are you with me? So this is one loss of capability. Now, we also know that wherever my peak is, there is going to be a distribution around it because of random fluctuations. I had hoped that this variation or the sigma of this distribution would be within 10% of my VT. But because of possibly temperature fluctuations at the time of manufacturing or something, it could happen that this is 15% of VT. Now, VT minus 3 sigma is VT minus 45% instead of VT minus 30%. Are you able to see this? Now reflect upon the initial exercise that we had done, जहाँ पे आपने equations बनाई थी, and then we said, okay, let VT be this, and now let us shift by plus minus 3 sigma, or let us shift by plus minus 4.5 sigma. And you remember what happened to your SNM and write margins, the stability, Vx, and writability? It's completely went for a toss. Now, if you, wherever your VT is, if this spread changes, again you are in a soup. So both these parameters jointly define process capability. Okay. When a new process is launched, for example, uh, they introduce a 3 nanometer process in your organization or a 7 nanometer process for the first time in your organization. Whenever a new process is launched, the process capability is bad. Then you practice and you observe spread or what is leading to this significant variation and where my lot is centered. And you start to tweak your process according to the machines on which you are processing. Okay? And then gradually you bring process under control. So there are these terms called CP and CPK. And they indicate that, for example, CP, I think this visual would be better. CP is about the spread that you have in your distributions. Okay. And CPK there is about the centering of the process. And you realize you need both of them. If you have a bad CPK, then even with a very good CP, you cannot do much. And if you do not have a good CP, even with a very good CPK, you cannot do much. Are you able to see this? So as if any one of you do go into a career where you're designing processes, which is very, very feasible now. So it was not feasible a few years later, but now it is very feasible with a lot of fab activity also happening in the country. So if any one of you do go into process technology design, this is something that you will see day in and day out. Even if you do not go there as a fab engineer, but you are a designer only somewhere, it is important to understand how the process is behaving. Because जो बात पहले हो रही थी that to mitigate the impact, you have to leave margins. So if my CP is bad or if my CPK is bad, I need to leave more margins. So what does this mean? This means that when I am designing something for the first time in any given technology and the technology is new, we know either CP or CPK or both are going to be bad. But you still want to give samples to customers. So you want at least some yield. I'm not talking about 100% yield, but some yield, some working sample should come out. So you will say, okay, my model is telling whatever, and my statistics tell me that I need to qualify 4.5 sigma to meet this customer's requirement, because not using itna bada capacity, just thoda sa usko sample kitna hi chahiye. And I'm not looking at 100% yield either. So what do? You say, okay, I really need to qualify only 4.5 sigma. But since this is the first design, this is iterative, and this is just to showcase something to the users, let me qualify 5.5 sigma. I'm designing with 1 sigma margin. Now, whether it is to be 1 sigma, or zero point 0.5 sigma, or 0.25 sigma, you will have to negotiate with your manager and your customer if you are the manager yourself. Hmm? But you need to arrive at what kind of margin you should leave. You may want to discuss this with technology teams also. What kind of margin should you leave so that you have required number of working samples with the customer? So it is very important. I'm not sure if how many of you have read anything about business, but जब आप किसी के साथ इस तरह का vendor agreement करते हो, तो there are milestones that you decide. You say, okay, upfront I will give you 20% of the payment so that you can start the work. आपने घर पे भी चूना कराया होगा. Something you must have got done at your homes. This is how the negotiation happens. Okay, take this much, start the work. Once these many rooms are done, I will give you another, 5,000 rupees. Once the second set is done, I will give you this much. So in chip design, 100 working samples is one such milestones. Are you getting it? That you deliver 100 working samples to me, I will release next set of money to you. So it's extremely important that you have those 100 working samples. So you may need to leave more margins, but you have those working samples delivered. Then there's another milestone which says that, okay, I want 10,000 working samples at the desired performance. So again, yield still is not targeted to be 100% or not targeted to be very high, but reasonable stable process and reasonably tight design means not too many margins left everywhere. See, आप हर तरफ margins ही छोड़ते रहोगे तो performance कहाँ आएगी? Variations have to be managed, but along with those variations, you also have to handle performance. So all these negotiations you will need to do at some point of time in your career. And it will change based on what is the maturity of the process there. Are you with me? So yeah, this is another view of that. Now, what is important to realize is that all the CP and CPK business that we just talked about, that is valid if you have a Gaussian distribution. But think about leakage. What is the formula of substrate leakage? Something, something, something into e raised to power VT, V minus VT and something. We're talking about exponential something there. Do you think Gaussian distribution will be valid? See, the basic processes are Gaussian. VT is Gaussian in nature. But the impact of VT on leakage is not linear. It is exponential. So other distributions also become relevant. Log normal distribution, Poisson distribution, extreme value distributions like Weibull and Gumbel, they become important in design verification processes that you will need to build there. Is that okay? So this is not a class on statistics or probability. So again, don't ask me a question, sir, ye kya hota hai? Find out. What I'm telling you is that statistics is an important field that you should be alert about, aware of. If you have not yet done a good course on statistics and you have an option or a possibility to do some course on statistics, I would say take it up. यहाँ के ट्रिपल आई टी के आपके सारे क्रेडिट्स पूरे हो भी गए हैं, pick up something online, pick up something. उसके 2 यूनिट्स मिले ना मिले क्या फर्क पड़ता है? What I'm telling you is it's important to understand statistics well so that you become a better designer. Okay? So when we look at mismatch, we have to ensure that the figures of merit of the SRAM cell, right margin, stability, SNM, all those things are statistically plus minus Six Sigma qualified. Hmm? Sense amplifier, we have talked about already in much detail. So I'm just Emphasizing it again for you. Sense amplifier, we already talked about common centroid, ताकि systematic mismatches आप ध्यान दे दो, taken care of हो जाएं. We already talked about where the offset comes from, and large SRAMs, large device sizes are used, large lengths are used so that the offset is minimized. We've also talked about the relationship between offset or the voltage that you give at the inputs of the sense amplifier and the reaction time of the sense amplifier. So all that has to be done through statistical verification. You cannot simply bring me one result and say, sir, this is my offset. I will say, okay, what is the sigma? And you will say, sir, मैंने तो single simulation चलाया है. सीधा zero. Are you getting it? So at circuit level itself, we are already saying that we have to take care of qualification of these circuits at plus minus 6 sigma or 4.5 sigma, depending on how many times that circuit is expected to be repeated in your designs. And now we talk about self-timing. See, हमने अभी तक हमेशा ये, we have already always said that when the sufficient differential will appear, the sense amplifier should turn on. अरे भाई, it's not going to happen अपने आप. You have to play that magic. Okay? You have to tell when to turn on the sense amplifier. Sense amplifier will turn on at some point of time, yes. But you have to ensure that that time, when you turn the sense amplifier on, is safe. So what are we saying? We are saying that, so याद है हमने जब पहले when we're talking about the data sheet, we said that in memories, we are self-timed. We just need the rising edge of the clock. Falling edge से हमारा कुछ लेना देना है नहीं. We will generate a reset ourselves. Why did we need to do that? Why did we need to do that? Independence from the falling edge of the clock, external clock?
So that we can operate at a slower rate of quantum gate.
So that we can operate at a different duty cycle than the external clock and therefore achieve faster frequency of operation. तो अगर आप इसी कोर्स के पहले सेशंस को अभी भूल जाओगे तो मिड सेम में क्या करोगे? इंटरव्यू तो मैं बात ही नहीं कर रहा, मैं तो मिड सेम जो अगले हफ्ते आ रहा है उसकी बात कर रहा हूं. व्हाट आर यू डूइंग? ठीक है. सो वी ऑलरेडी सेड देन दैट वी विल जनरेट द रीसेट आवरसेल्व्स. दैट इज व्हाट इज सेल्फ टाइमिंग. व्हेन दैट रीसेट कम्स or we generate that reset so that this reset also triggers a sense amplifier. This reset generation mechanism is what is called as self-timing. The memory times itself, therefore self-timing. And self-timing appears something like this. See, abhi tak, this was what you saw. And somehow magically SAN appeared. Now, for self-timing, what you do is you take the clock to one extra row to generate a replica word line. That replica word line discharges what is called as a replica bit line. So this is replica row decoder, replica word line, and replica bit line. And then at the end of this replica bit line, you put a, obviously now, agar yahan pe sense amplifier lagaya, to what will trigger that then? Doesn't work. So you have to put some other digital circuit here. So you put a inverter here. And when you say that when this inverter gives an output, that will trigger the sense amplifiers and that will trigger the reset of the memory state machine also. So this replica path is extremely important for both read cycles and write cycles. So until now, what we had looked at was CK2 word line generation. We said word line XDEC clock would come and it would generate a word line. But now I've added another brown signal there. I'm saying it will also generate a replica word line. Now, do you realize when I say replica, I've put it at the top of my array. You may put it in the middle of the array or bottom of the array also. Okay. Whichever way you do, you should know what you are tracking and what you are not tracking. That much clarity you should have. I've just, in a cartoon way, put it on the top saying that पूरा row decoder का जो delay है, that is also tracked. So that my word line and replica word line get selected at the same time. Then bitline also I put at the fag end and I said, okay, bitline का पूरा delay track होगा. And then मैं ऐसे ही इनको लेकर आया. So what does this ensure? That the cornermost sense amplifier has the minimum requirement of the offset, but the sense amplifier, which is right next to the control region, would get a lot of differential at its inputs. Do you realize this? Because let's go to the last slide once again. See, what did we see there? This particular sense amplifier or this particular inverter will get triggered after my worst case cell would have been triggered. Am I right? So, and I'm saying that when the first sense amplifier right next to this particular trigger signal is activated, it should also have sufficient differential at its inputs. Now consider a memory cell over here. Now this memory cell was selected much earlier than the replica word line was selected. And this memory cell or the sense amplifier in this location will get triggered much after this one, which is on the corner. Are you able to see this? So this particular memory cell will generate much more differential than the one in the corner. So what we have essentially ensured through this mechanism is that my cornermost sense amplifier is the worst sense amplifier. Now imagine it differently. Suppose I had put the replica bit line somewhere in the center. I'm not saying do it. I'm saying suppose I had done it. What would have happened? I said my replica word line is somewhere in the center. Now my trigger of the sense amplifier would come somewhere here. And where are the worst cells? In the center. If I would keep this replica bit line in the bilkul adjacent to my control region, where would be the worst cell? Right adjacent to the control region. Because this is the path of the activation signal. Are you getting it? So where you place your replica bit line or replica sense amplifier will define how much margin you have in which particular cell. So now when you are verifying your design, do you realize it is not necessary that this is the worst case cell or this is the worst case sense amplifier? Depending on where you placed your signals and what kind of tracking you did, the worst case could be right adjacent to the control region also. So again, because आप कहीं और पढ़ोगे कोई किताब और कहोगे कि अच्छा the farthest memory cell or the farthest sense amplifier is the worst memory cell. I'm already breaking that notion for you. It changes based on design. It changes based on the architecture. It changes based on the way you have done the tracking of your system. And you better be alert about it. Otherwise, whatever you design will start to fail. And a silicon failure is a very expensive failure, not just for the company, for you as an individual also. आप सीखोगे, लेकिन वो कुछ ज्यादा मुश्किल हो जाएगा सीखना. ठीक है? People lose jobs because of silicon failures at different levels. Not the youngest designer will lose their job if their design fails. But yes, the manager in the team may lose their job. So silicon failure can be a do or die thing. So you better Analyze your circuits for the verification purpose extremely carefully. Design verification is an extremely important job of a VLSI designer. Okay. Now, this is not the verification engineers जिसकी jobs आती रहती हैं. Those verification engineers are about STA and other verifications at the SOC level. I'm talking about design verification at circuit level. These jobs appear as memory designers only. So as memory designers, you do not only design, you also verify the design. Are you with me? So we generate the replica word line also. That replica word line generates the reset signal, which would then generate the reset of clock internal and everything else. So अभी तक हमने ये बात करी थी कि memory speed is determined by when my read completes. Now I'm saying no, memory speed is also dependent on when my reset comes and I'm ready for the next cycle. So while access time, that is T, the CK to Q delay is very important, the cycle time, that is when is the next clock that I can bring, is also very important because that will define the frequency, max frequency at which your circuit can work. And that is determined by how you have designed the reset signal, how much margin you have left in your replica path. Are you getting it? So you want the replica path to be safe, but you cannot have too much margin left there. Otherwise, performance will go for a toss. Are you getting it? Now, this was for the read operation. Similarly, for the write operation, you have this reference word line or replica word line, replica bit line, and you have a write detect signal that comes when your replica memory cell is written into. Okay. And once the write detect signal comes, you trigger the reset, and then that resets the entire memory. Is that okay? So another look at mismatch when we talk of SRAMs. अभी तक हमने खाली क्योंकि मेमोरी सेल्स ही देखे थे और सेंस एम्पलीफायर्स पे ही इतना डिटेल डिस्कशन करा था. The first look that we had, we talked about various figures of merit. You have to do Monte Carlo, you have to do this, you have to do that, all of that. But now I'm saying there's more to it than that. We're talking about replica array and memory array. So याद है मैंने environment cells की बात करी थी? Do you realize these replica bit lines and replica word lines also need that same environment? So they are actually right next to, or you may say inside the memory array itself. And those environment cells are beyond these replicas. Okay, that is one thing. And you have to ensure similar metal structure. मतलब वो आप अगर replica bit cell देखोगे, replica word line देखोगे, आपको फर्क ही नहीं पता लगेगा. Unless you go into detail with the lens in your hand and say, okay, where are my VR2s which are connecting the word line to the gate there? So you will say, oh, in this particular word line, VR2s don't exist. So this is a replica word line. Oh, in this particular word line, in this particular row, the connection to the bit line is broken. That VR doesn't exist. So this is my replica bit line, a replica line or replica column, and things like that. So you have to go into that detail to be able to identify कि कौन सी ये replica है. Otherwise, everything else is same. All metal, all the topology is exactly the same. That is what you have to ensure. If you do make any variation, for example, you need to program something inside the memory cell. You can't change metal ones, you can't do anything like that there. So what you will do, you will extend the poly out. Just poly को थोड़ा सा extend करोगे. And then you will do something outside the memory cell. Nothing inside the memory cell. Okay? So if any one of you takes up a project on designing these replica cells, that could be a very interesting learning exercise to understand how this matching is done and ensured. Similarly, the replica row decoder has to be very similar to the real row decoder. Now, it's not easy because in a real row decoder, you have those NAND gates and you have, we talked about making 4 rows in one row decoder. But now you only need one replica word line. So there are bound to be some changes, but you still have to ensure and try and get as much matching as is possible. Definitely, the replica word line and the word line have to run in the same metal layer. All the systematic variations, whether it is proximity effects or STI or anything, you have to somehow replicate all of them for the replica decoder also. Is that okay? And similarly, the same constraint that if your precharge is to track the word line and word line is in metal 3, then your precharge signal also has to be in metal 3. Your write clock also has to be in metal 3. So the same thing applies to any other signal which you want to somehow match to your real access path. Are you getting it? So matching is an extremely important aspect of memory design. And you use a wide range of statistical methods. Monte Carlo, you already know. Some of you have already done Monte Carlo for power analysis. No, power analysis, we don't need Monte Carlo analysis yet. But ensuring that my SNM, my right margin are Six Sigma qualified, the offset that I estimate for my sense amplifier is at 3 sigma or 4.5 sigma as the project specifications decide, and all those things, you will need to run Monte Carlo anyways. Okay. Now, one thing that you need to realize is that Monte Carlo is a uniform distribution kind of a mechanism. वो क्या करता है, उसको अगर बता दिया गया कि this is a Gaussian distribution, it will uniformly distribute samples across that Gaussian distribution so that you get to see worst case results also in one of your simulations. Hopefully. It's always hopefully. There's no deterministic thing in it. Okay. So we, as designers, started to evolve other methods than Monte Carlo, where one of the methods was importance sampling, where we said that, okay, let me run first 50 random simulations with uniform distribution. And because I have varied 10 parameters across these 50 simulations, I will see which of the parameters, variations in which of the parameters impact the variations in my output more significantly. So I find the sensitivity to variations in inputs. And then I say, okay, inputs to which my output is more sensitive, I will vary them more. I will select more around that vicinity. So I have first, through a few random simulations, identified worst case region. And then I have done more and more simulations in that worst case region than the entire distribution. With the hope, again, hope, that I will now be able to see at least one worst case simulation in my 500 Monte Carlo runs also. Again, it's a hope because the process of picking up those variations is still random. The tool does it without really understanding the circuit. You just put in some machine learning into it. So for design verification, sample and importance based Monte Carlo was the first machine learning implementation. आज आप देखोगे कि बहुत सारे लोग कह रहे हैं कि machine learning के basis पे verification करना चाहिए. But this was proposed way back, even before AI was that big a buzz. It was kind of a struggling research area. At that time, we were already talking about sample importance sampling in memory verification. Okay. And the third method is design of experiments. Over here, what you do is you do not do random parameter selection. You say, okay, I know that the SNM of my memory cell is dependent on the VT of the pass gate and VT of the pull down. How do I know this? Because I know my circuit well. See, Monte Carlo is to be done when you know nothing about your circuit. Black box. Anyways, you will do Monte Carlo. Even if you know something about your circuit, you might not have all the insights required. So Monte Carlo you will anyways do. Importance sampling is an advancement of Monte Carlo, which your tool can do based on, again, what measurements you want to measure. It will do something and identify which samples could be more important than others. In design of experiments, you need to analyze your design first in advance. So you need to be very, very good friends with your circuit. It cannot be like a black box for you. And then you say that, okay, I know that my pass gate and pull down are the ones that are going to impact my SNM. Pass gate being fast would degrade the SNM, would improve the SNM, and pull down being slow would degrade the SNM. So you say, okay, मेरा pull down का जो VT है उसको पॉजिटिव की तरफ लेके जाओ, उसको VT प्लस 1 सिग्मा, 2 सिग्मा, 3 सिग्मा, 4 सिग्मा, 5 सिग्मा रखो. बाकी सारे डिवाइसेस के VT को नॉमिनल पे रखो. Let me see the sensitivity to the VT of my pass gate, pull down. You do a similar exercise for pass gate. You do the similar exercise for pull-ups. You do similar exercise for your sense amplifier. So what you're doing is every device in your circuit, you will every other device in your circuit you will put at nominal. Just one device you will pick and take it to deterministic 3 or 4 sigma variations. Essentially identifying the sensitivity of my output parameter to these input variations. Are you with me? And then once you've done that, you say, okay, now since my output is dependent on these 10 variables with different intensity, I will put a different weight on variations of pull down, a different weight of variations on pass gate, a different weight of variations on pull up, and so on, and then give you one vector that, okay, pass gate is at 4.5 sigma, pull down is at minus 3.2 sigma, pull up is at plus 8.8 sigma, whatever. Okay. I will give you some vector of variations of different devices. And when you now run one single simulation, you will be able to see the worst case waveform. You will be able to see how badly your system is failing or how marginally your system is passing, whichever the way it is. And if you qualify this particular vector, I can assure you your system will work. No longer 500 or 1 million simulations. Just a few hundred simulations, and you have the worst case vector available to you. Is that clear? So that is what is design of experiments for you. Design of experiments was a technique which was not really originating from VLSI. It was design of experiments people have been doing. Scientists have been doing design of experiments for a very, very long time. It was just that it was formalized for VLSI implementations sometime around 2010-11 timeframe. And today there are very powerful tools like Solido and others from everyone. Siemens के पास भी है, Cadence के पास भी है, Synopsys के पास भी है. Each one of them have their design of experiment tools. They are hugely expensive, but they are now available in the market and industry does use them. Because they are very expensive, you don't just launch everywhere. You first do the first level of verification yourself, ensure things are fine, and then final sign off you do with such tools. Okay. So it is 12:20, but if you give me 5 more minutes, I can introduce the topic of redundancy to you. Can I take 5 more minutes? Is it okay? It's entering into your lunchtime, I know this, but is it okay? 5 minutes? Huh? So, see, we have always said that memory cell layouts are very, very dense. We have said that we will do a lot of sharing of devices, structures, contacts, vias, everything across the memory cell boundary. So that when we talk of an array, there are many structures of which some are at one boundary or another. And with so many contacts, VRs, everything coming into picture, there's a possibility that one of those contacts or VRs can fail. So there's a possibility that one contact fails, but that particular contact or VR is in the center of the memory cell. So one defect will lead to one failure. However, if this particular failing cell was at the cell boundary, I will have two cells which are failing, whether it could be across two rows or across two columns. And there is also a worst case possibility that this one fails. So one single defect, and that leads to four failures. Are you able to see this? एक डिफेक्ट आया बट चार मेमोरी सेल्स फेल कर गए. Two rows or two columns may start to fail. And you will notice that when you manufacture or when you start to test SRAMs or uh, structures like this, you will see that many failures are single bit failures, which could be because something internal to the memory cell failed, or which could be because of SNM failing or writability failing or anything. Now you can't tell much about it. But there are many failures which are dual bit failures, vertical bit or horizontal 2 bits. And there are many quad bit failures also. So the signature of failure tells you which structure is failing, whether it could be a design failure or if it is definitely a technology failure. So if you hear about a vertical 2-bit fail or a horizontal 2-bit fail or a quad bit fail, you're sure it is a technology feature. But if you see a single bit fail, you can't be so sure. So for a single bit fail, you will need to do more testing. You will probably want to see the circuit at higher voltage or lower voltage and see if that single bit fail is recovered. And many times you will see those single bit failures will be recovered. What that means is this is a failure of your design. That you did not leave sufficient margin in your SNM or write margin or somewhere else in the system, because of which that single bit failure is happening. But for dual bit and quad bit failures, they are clearly a process related fail. That is a clear thing. Are you with me? Is this part clear? So process teams insist that to have good yield on memories where we are violating so many DRCs, we should have some redundancy, some repair cells which can replace technology related fails. See, a technology related fail doesn't mean technology is weak. It means that so many things that you did beyond the DRCs, anything of that could have failed. So the probability has already increased for you because you did DRC violations. So you better keep some extra repair elements in your system so that these vertical bits, horizontal bits, and quad bits, and even single bits, when they are coming because of process, should be repairable. Is this part clear? So for every technology, there would be some rule that if you're using 32 megabit, then at most 16 megabit can be non-repairable, but you have to maintain 16 megabit memory as repairable in your system. So what does repairable and non-repairable mean? Repairable and non-repairable means that if this is the red bit which is failing, okay, I should be able to replace this red bit with an alternate row somewhere. So when I'm talking of row redundancy, so that for a user, this red bit doesn't even come into picture, it's blacked out. If someone sends me the address of this red bit location, instead of going there, I will select this repair element. Are you getting it? So this redundancy is therefore a very important part of our memory design. That these repair elements have to be built in even before your first silicon goes. Is that okay? Now, what do you need to add? Do not need to add just the extra rows. You also need to add some comparator logic, which would select this extra row depending on the address that is given. When the address is related to one of the failing rows, it would select the repair rows or the redundant rows. Stepney. You know what a stepney is? Who doesn't know what a stepney is? You do not know what a stepney is? So, in cars, on scooters, there is an extra wheel that is put so that if you are traveling somewhere and one of your tires gets punctured, you can use that extra wheel and continue your journey. So this is something very similar to a stepney over here. Okay, that if on silicon some circuit fails, some itself fails, you don't need to reject that particular die. You can recover the yield. You can still continue using that same die by using these repair elements. Is that okay? So now when it comes to row redundancy, do you realize that in my address path, I have now added one comparison there. So which timing will get impacted? Setup time. Because now my address has to go through another set of logic before it can mix with the clock somewhere. What is the impact on excess time? Almost nothing. Almost nothing. Practically nothing. See, you have some extra bitline patterns, all that. That is a minuscule thing. That will not really bother you much. But when you use row redundancy, address setup is impacted. Okay? Suppose you are very sensitive to the address setup timing. You say, no, 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 no. Address setup, I can't increase. Then there is also an option to use what is called as column redundancy, where what you do is instead of replacing two rows, you replace a bit slice or a set of columns. And the process is that you will disconnect that particular column and reconfigure every other column ahead of that particular column to use the right output there. See, in row redundancy, it was so simple. एक कंपैरेटर डाला और कुछ भी नहीं करा मेमोरी में चेंज. यहां पे मैं कह रहा हूं तो फेलिंग कॉलम के बाद आपको सारे कॉलम्स को रिकॉन्फ़िगर करना है. व्हाई? I can have an extra sense amplifier and write driver in my last column also. What's the problem? I will also have redundancy for the sense amplifier that way. This is not about the sense amplifier or the write driver. In fact, if I repeat the sense amplifier or the write driver, I will have redundancy for sense amplifier. कोई sense amplifier बहुत खराब बना, मैं उसको भी replace कर दूंगा. Why do I need to do all this jugglery? To maintain the mux नहीं, mux को फर्क नहीं पड़ा. अरे आप लोग तो VDF कर चुके हो. Think at the chip level. How is the memory used inside a chip?
So you pass an address.
You put in an address. So on a chip in the physical location, there are some places where the address pins will go. And there are some locations on your device, on your memory, from where you will draw out the output. Now, because some particular column failed, can you change the place from where you will draw the output now? Is the metal physically connected there, is it not? So that Q8, if that Q8 was failing because of a bad bit cell, that Q8 still needs to arrive there only. It now cannot arrive at the end of my array. It has to arrive there only. So what do? You say, okay, this particular column is failing, this particular queue is failing. I will reject this queue, but इसके साथ वाले को यहाँ पे लगा दूंगा. Then उसके साथ वाले को उधर लगाऊंगा. And that is why all this jugglery. See, in row redundancy, we talked about a equal to comparator. Whenever the address is equal to this, use the repair row. What kind of a comparator you will need here? You will need to compare a failing address with your address, na? So what kind of a comparator do you need here? अरे तो बेसिक इलेक्ट्रॉनिक्स का सवाल है. What is the logic that we are applying? Yes, you will need comparators on the columns. What will they compare? I tell you that column number 158 is failing. And you have to tell me whether you have to shift or not shift. So what kind of a comparator do you need now? You have 1000 columns in your memory. I have told you one column number 158 is wrong, is failing.
So you just need the equality comparator, right?
So if I have an equality comparator, then there will be no shift output coming out at column number 159, no shift output coming out at column number 160, no shift output coming at column number 1000. Is that what you're looking for? What is it that you're looking for?
So if your column is greater than that thing, then you will have to shift the output from the next column.
Is greater than sufficient? So Madhav is saying if the output is greater than the failing address, then you have to shift. Is that sufficient? Greater than equal to. Now, do you realize that the comparator is far more complex in column redundancy than in row redundancy? An equal to comparator is just a set of XOR gates. A greater than equal to comparator is complex. It's not just XOR gates now. Every column has a different programmation because every column has a different address. So designing the comparator in a column redundancy is a very complex thing. But we do it. As a designer, if you have to recover that yield, you have to do it. The benefit is that there is no impact on setup time. And there is a very minuscule impact on excess time. Very minuscule because you just had a little extra RC to go from one particular IO region to the other IO region. So very limited impact on excess time. So almost no timing impact, but area impact is huge because now there's a very complex comparator there in every column or in every IO. Whereas in row, there's one equal to comparator, a small comparator, and that too only once. Sufficient. Tha. So column redundancy comes at a larger cost in terms of area, but equivalent performance as original design and equivalent power as original design. So whichever, देखो कभी भी आपके पास design choices आएंगी, you have always to compare them on at least P, P and A. Are you able to see this? This analysis you should always be able to do. This is extremely important. So there is nothing like column redundancy is better or worse. You could use bit size redundancy and the size of your comparator immediately reduce. But somewhere else you will need to give up area. So you may get a googly question in your interview even in the mid-sem exam. But you have all the tools to be able to analyze them and come up with an answer. So ratte marne ka fayda nahi hai. It is important to understand the concept so that whatever is thrown at you, you're able to handle it well. Is it okay? So we'll stop here and we'll start with caches in the next class. All the best.